6.1, which is exploring accumulations of change. So, what we've been doing when it comes to differentiation is that we've been given uh, a function, and then we differentiate and we get something about the rate of change of that function. So, like, to go back to review, if we have, for example, the position of something over time, right? So this is our review from before. This is S of t, let's say. And then this is along t, and then you have something that looks like this. You have some curve. If you wanted to find out the instantaneous rate of change, right, you would take the derivative, which would be the slope of the tangent line. Now, in this case, we're going in reverse. So from here, we get, right, S of t, S prime of t, where S is the displacement of this thing, is the velocity. That gives me the rate of change, right? And I get, from this, I differentiate, right? I differentiate, and I get the rate of change from the position. We want to go in reverse now. We want to see what I can get about the displacement given the velocity function. So if I'm given a velocity function, something like this, let's say, up here, so let's not even bother, how do I go and how do I get something about the position? So in this case, right, just think about this example as a whole. If you're going 10 meters per second, something is traveling, I don't know, who cares, whatever. Something is traveling at 10 meters per second, okay? And that's right here. This is at 10 meters per second. This is the velocity. And it does that for 7 seconds. How far did that particle or that object or the bicycle or whatever, or the car or whatever, anything, how far did the particle travel? Did the object travel? Whatever it is you're talking about. Well, 10 meters per second for 7 seconds, that's a simple thing. All you would do is you would do 7 times 10 meters per second. That's just as simple as velocity equals distance over time. You want distance, so it's velocity times time is the distance. The velocity is 10, the time is 7, so then therefore the displacement is 70, or S if you want displacement, right? And we're going to see the difference between distance and displacement in a second. Yeah, you could say displacement is S, but the whole thing here is that there's a geometrical interpretation. So we could see that the distance is then 70 meters because we did this algebra. Velocity is equal to displacement over time, or change in displacement over change in time. And then I multiply and I get 70 meters. Again, that should follow from our intuition. Something's traveling 10 meters per second for 7 seconds. So every second it goes 10 meters for 7 seconds. The whole thing is 70 meters. Now, the geometrical interpretation, if I have the graph of velocity and I have it mapped over time, right, so time is on x and then the velocity is along y, then we should see that that 70 is actually just the area of this rectangle. The area of this rectangle is 70 meters. Right, and that's a little strange that the area represents meters, which is meters squared, but we shouldn't have too much of a difficulty understanding that this area is in fact the actual displacement of the particle. And that's going to hold true even when the velocity is not constant or the rate of change is not constant. So this is going to apply for any rate of change function that we have along here. We can get the area, and that's going to give us the displacement or the amount that actually changed. So a good example is, let's say A of t represents the altitude of a drone or something. So change in altitude of a drone, change, or rate of change of altitude, let's say. Rate of change of altitude. So there's some drone or whatever, something flying upward. altitude, rate of change of altitude, is A of t, and you see that at the beginning, the altitude, it originally starts going up at time 0 at 8 meters per second. Then it slowly goes down, and then what happens at 8 seconds? The altitude of this drone goes to 0, so it stops moving up at 8 seconds. And then it begins to move down after 8 seconds. And then it begins to go, what happens here? Well, then it begins to go down, but it begins to slow going down, and then it goes back to being 0. So the question would be, what is the altitude of the drone after 12 seconds? Or what is the change in altitude of the drone? Because we technically don't know how high the drone is. But let's say that the drone started off at the floor. So it started off at 0 meters high. Okay, what happens? Well, then it goes up at 8 meters per second for a long time. It slows down until it's at it goes 0 meters per second up, and then it begins to go down, right, all here from 8 seconds. It begins to go down, and then it slows going down till right here until eventually it stops. And we want to find out the final altitude at 12 seconds of this drone. So at this point right here, I put this says -3 meters per second. But okay, so let's figure it out. How can we do this? Well, let's find out how high it goes to the 8 seconds. So how high does it go at that 8-second mark? Well, it goes 8 meters per second, and then it goes down to here, and all you need to find, just like in the previous example, is the area of this triangle. And then that'll give us how high it is at 8 seconds. How high it is at 8 seconds is 8 times 8 divided by 2, because that's the area for a triangle, just 32. So it's 32 meters at 8 seconds. That's how high it went. Then it begins to go down all here. All in this region, the drone is traveling downward. And we need to find out that area that it goes down, right? It goes down in that portion. So what's this length right here for this? It's from 8 seconds to 12 seconds. So that length is 4 seconds. And then now what's the height of this triangle, or the altitude of this triangle, is 3, because it's 3 meters. So it's 4 times 3 divided by 2. That's 12 divided by 2, that's 6. So it's minus 6 meters. And it goes down in that region, and 32 minus 6 is going to give me a total of 26 meters. And it winds up at the 26 meter mark right here, assuming that it started from the ground at this point. Assuming at time equals 0 is on the ground. But it changed a total of 26 meters, wherever it was. If it started at 10 meters in the air, then it still changed. It went up to 36 meters at the end of this, if it started at 10 meters. Okay, if we assume that it starts at 0 on the ground, and then does this whole thing, then it's going to wind up at 26 meters in the air. But it could have started at anywhere in the air. We don't know that. We don't know that information. But assuming, again, it started at 0, then we know that it winds up at 26 meters in the air. And again, this is just going to be it going down in this region. It stops going up or down at these points where it crosses the 0, because A of t is the rate of change of the altitude.